and not in the continuous time domain, the analog domain. So we are going to look at, of course, this is what you are familiar with, the mathematical, the convolution. This is a discrete time convolution. This is a continuous time convolution, yeah, and that is a convolution operation is represented with this symbol here. And of course, this means the linear convolution. We are going to look at both linear convolution and the circular convolution. Yeah. So of course, this is the that's a symbol, but of course, it's that symbol. What symbolizes is actually this operation. Yeah. That symbol, the actual mathematical operation is this one. That's the y of t is the integral from negative infinity to infinity x of tau. Yeah, I think it's good to really understand because you're talking about x of tau. Yeah, this is a time difference. H of t minus tau, the time difference, d tau. Yeah, that is the integral. Sometimes you can confuse this with the coordination, because the coordination again has almost a similar operation. Of course, in that one, the y is you look at y, how it varies with tau, yeah, with the time difference. And of course, what we have here is x of n, and this is h of n, yeah. Yeah. And so it will be a bit different, yeah. So it's good to get to understand this. How convolution. We are going to look at actually later at the discrete convolution function. Yeah. So that is the convolution time. Convolution. That's the continuous time convolution. But we are going to concentrate more on the discrete time convolution. And so you are given two sequences. And of course, one sequence is your input, the yn, and this other sequence is the impulse response. What you are seeing is this sequence is the output of the LTI system when you give it the impulse signal or the unit sample signal. Yeah. So usually it will be having, if you put in a system 1 pulse, the output will not be 1 pulse. It will be a sequence of those impulses. It will be a sequence of time discrete deltas. Yeah. So that's the one it is replaced by. Well, it may even be scaled also. Yeah. Yeah. So that is what we are saying for an LTI system. This operation gives us the output of the system. Yeah, I think we know that, but I don't get tired of repeating it because of the importance of this. So y of n is equal to the summation of k from negative infinity to infinity, h of k, x of n minus k. But usually these sequences are just finite sequences. So, of course, x of k and x of n of k are 0 outside their defined intervals. And of course, this can be x of n, h of n minus k. It will not change anything. Yeah. with convolution, it doesn't change. Of course, with correlation, it does change, depending on, because with the correlation is not, which term do you use? Once the order of this, of course, it changes the output completely. Yeah. But with the convolution, it doesn't matter whether you start with h of k or n of k, whether it is h of n which you minus the k, or is the h of k. Whether it is x of k or x of n, it will be the same thing. So we are going to look at how you work out the discrete time convolution using different methods. And of course, I think I should start with the easiest method. This is not the easiest. I will start with the easiest, and then we go to this other method. Because sometimes, if you are not sure of this method, or rather, even if you do it with this method, it's always good to come to check your answer with the easier method, especially for short sequences. Yeah. So the easiest method, of course, is what you call the tabular method. This is the tabular method. So you are given two sequences. Your two sequences are 1, 2, 3, 1. Yeah. And we said if you are not given any information, if there is no arrow in your sequence, then it means this is a zeroth sample. So this is n is equal to 0. This n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3. And this is 0, 1, 2. Of course, if there was an arrow, then this will be -1. If there was an arrow here, for example. For example, if this arrow was here, then of course, this will be where n is 0. So the zeroth sample is 2. Yeah. When it's not given, the zeroth sample is the first sample. Yeah. So you are asked to find yn. So it's important to know that you have two sequences, one of length L. So L here, let's say this is the first sequence. L is M. L is the length of xn. Then the M is the length of the other sequence, which is a sequence h of n. So this has got 4 samples. Yeah. So n is 4, and this n is 3. Yeah. I think somebody is trying to come. Sorry, I thought I saw like someone is trying to have a weird screen. Yeah. So here we are saying the length of the output sequence, the length of yn will be L plus M minus 1. So if the first sequence starts at N1 and now starts at N2, the output sequence will start at N1 plus N2 and end at N1 plus N2 plus L plus M plus minus 2. What we are saying here is if one sequence starts at 0, another one at 0, then the length of the sequence will be 0 plus 0 plus 4 plus 3, that is 7, minus 2. So it means the length of this sequence will be something must be wrong, because where it ends, it starts at 0, 0. This formula is not agreeing. I think this must be 1. Because the length of sequence, well, it's all right, it's okay. It's minus 2. Yeah? is minus 2 because it is going to end at y5. Yeah, that's what we are saying here. We are saying it's going to be, because remember there is from y0, that's why we are having the 2. And there is the length of the sequence itself is L plus M minus 1, but where it actually ends is at minus 2. Yeah, because I think you understand that. Because if this means this is 4 plus 3, that is 7. But so it is going to be 7 samples. Those 7 samples will be y. Oh, no, 7 minus 1. So it is 6 samples. That will be y of 0 up to y of 5. That is the 6 samples. That's what we are saying, that it is going to end up at L plus M minus 2. If it was starting here, I mean, if this was a 0 sample, so it is starting at minus 1. So this would have been minus 1 plus 4 plus 3 minus 2. So it will be, well, the start will be this, n1 plus n2, which will be minus 2. And it will end at minus 1 minus 4 plus 3. Yeah, minus 1 plus 7 minus 2. So this will be plus 3. So the output will be y to the y of minus 2 all the way up to the y of plus 3. I hope we understand that. Whichever method we use. Yes, Sherry.
Could you please repeat why the output becomes L plus M minus 2?
Oh, why it becomes minus 2? Thank you. It's because we are not, although the length is L plus M minus 1, you see the length is N, but where you start is not 1. You see, this is 1, 2, 3, 4, but we don't start with 1, we start with 0. So it is going to start. So why this is minus 2 is because of I'm trying to explain the best way. You have 6 samples. When you have n samples, it means you start at 0 and end at n minus 1. So if you are going to have L plus 1 plus M minus 1 samples, you are going to be ending at L plus M minus 1 minus 1 because of the n minus 1. Did that answer your question? Sherry?
Yes.
It did. Thank you. Yeah. So that's it. So let's look at examples. We will look at the straightforward example whereby it starts at 0. So these are your 2 sequences. That's it. Yeah. And this is region 1 minus 2, 1. That's the way it is. So this is h of n and this is x of n. It will not make a difference if you put them the other way around. Yeah. So this one, this will of course just be 1 minus 2 plus 1. This is 2. You're just multiplying all this with 2. So it is 2 minus 4, 2. You're multiplying all this with 3. 3 minus 6, 3. And you're multiplying all this. So this is just the same as this row. This row is just the same as this row. Then what you take to be your y is y of n. Of course, y of n is simply, we know it will be y of 0, yeah, because we are starting at 0, n1 plus n2, 0 plus 0, y of 1 plus y of 2 plus y of 3 plus, remember there are supposed to be 6 samples, 1, 2, 3, 4, 5, y of 4 plus y of 5. And what we are saying, this is y of 1, because this 1 is just alone. Y of 2 is 2 minus 2. I mean, it's 2 plus minus 2. So this will be 1. This will be 0. This will be 0. This will be, yeah, because it's 3 plus 1 minus 4. This will be minus 3. This will be 1. And this will be 1. So this is will be output. So what we are saying is, if you have a system that gives you this sequence, when you give it the unit sample, if you give it this sequence, it is going to give you output. It is going to output this sequence 1, 0, 0, minus 3, minus 3, 1, 1. Yeah, and this is important to know that this L, because this L plus n minus 1 will keep on appearing in whatever method you are going to use to do, so long as you're doing linear convolution. Yeah, it's good to understand that. So long as you're doing linear convolution, you always get that. Yeah, if you are doing circular convolution, we will see that. Yeah, so is that method is straightforward, is very easy to do. The one where I find most people have got issues is the graphical method. So graphical method, what we do is we take the two x n and I of n, we change the variable from n to k. Yeah, so we have x of k here. Just this is a graphical. I'm putting this graphically, starting from 0, starting at 0. So this is a 0th sample, this is the first sample, second sample, third sample. And then we have here h of k, yeah, the same way. But now what we do, remember in this equation has got x into, oh, here I think we have used h of k, okay. Actually, in my example here, I have done the h of n minus k, yeah, which will give the same thing. Here it is x of n minus k, but here I've used h of n minus k. So that is h of k. Then, of course, what we want is n minus k. We want h of n minus k. So we are going to plot h of minus k. So that is h of k. This is h of minus k. So we have simply it's just a reflection along the y-axis. Yeah. So that's it. So this is your h of n minus k for n is equal to 0. That's what it means, isn't it? Yeah. This is h of k. So now here we start to find our y of 0, because y of n is y of 0 up to, these are how many? 7 samples. Up to y of 5. So this 7 minus 1, 6. So it is y of 0 to y of 5. So this h of minus k, which of course is the same as h of n minus k when n is equal to 0. Yeah. When you put this is equal to 0, it's just the same as this one. So you come and put your h of n minus k. And then we just do point-wise multiplication, because that's what you are doing here. You are simply multiplying this and this at different values of k, and then summing, doing the summation. You are multiplying this at different values of k to get n. Yeah? Yeah, because n, for each of n, that's what you are doing. You are moving from negative infinity to positive infinity. What that means, it means, yeah, you are multiplying and then moving. So what you are going to do is, that is, when n is 0, it will simply be the same graph here, isn't it? So when n is equal to 0, you get that, for h of n minus k. That will give you, when n is 0, of course, you get the y0. Yeah? So you begin doing point-wise multiplication. So it means the one that corresponds, this corresponds to this corresponds to this corresponds to this, corresponds to this. It may not look so, but it is supposed to be that. Yeah. So this is 1 times 0. Yeah. Is 0. So this is simply 0 plus minus 2 times 0 plus 1 times 1 plus 2 times 0 plus, oh, did I jump something? 1. Oh, I should do this. Yeah, 2. Then, so that is 0 plus 3 times 0 plus 1 times 0. So y0 is simply 1. You sum them, yeah, because of the summation, yeah. So y of n, so when n is equal to 1, this works out to 1. Then we slide this to the right, so that now n is equal to 1. So you're going to get of h of 1 minus k. So that's what we have done here. We have x of k. Now we have h of n minus k when n is equal to 1, which is actually h of 1 minus k. Yeah. So this actually is h of 1 minus k. Yeah. And you do the same math again. So this corresponds to this corresponds to this. Oh, sorry. I think it's always good to start from here. This corresponds to this, therefore this corresponds to this corresponds to this. And you can see what happens. This is simply 0 times 0 is 0, 0 times 0, 0 times 1, you don't even look beyond 0. Actually, you are supposed to start from here. Forget this one. So this is 0 times 1, because it is 0 outside those limits. Yeah. So this is 0 times 1 is 0. 1 times minus 2 is minus 2. 2 times 1 is 2. And all these others are 0. Yeah. So that gives us 0. Then we move to the right. Yeah. We move to the right. We have this. You move 2 steps. So h, this is h of 2 minus k. Yeah. So I don't think we even have to continue. Now it is, I think you get the crux of the matter. So okay, so we multiply this. This gives 1 plus minus 4. This 3 times 1 is 3. And so then others are 0. So that is 1 plus 3 minus 4, 0. Yeah. I think I've used the same one below here. Oh, I use the same, yeah, I use the same one. So it should give us the same results. So that is 0. Then we come to this one. We are just sliding to the right until they are not overlapping anymore. Yeah. So now we are here. I think this is where we are. So again, this is 2 plus minus 2 times this minus 6, and this is 1. So that's minus 3. Now we're almost completely getting out of, well, there are still some overlaps. These two are still overlapping. So this is 3 times 1 is 3, and this plus 1 minus 2 is, that is minus 2, that is 1. And then this one, of course, this one is only this one, which is just 1 times 1. After that, there is no more overlap. Yeah. So those are your samples. And you can see it agrees with what we got with this method. Yeah. Yes. So are there any questions with the graphical method? Yeah, so linear convolution, those are the two, we will learn those two methods, the tabular and the graphical. Yeah. I think we are going to have, what I normally do is, we just look at what is in the notes. Later we'll come up and for 1 hour, we can do now more examples of this. Yeah. Then, so that is linear convolution. But we also look at circular convolution. And circular convolution is important because of periodic functions. When it comes to periodic signals, you find there are a lot of let me admit some people. Okay, there will be a lot of overlaps. Yeah, because you can imagine when you have this convolution, you can see that you have more than the number of output samples are longer than they're longer than either of the sequences. So if they are repeating themselves, that part which is longer will begin overlapping with the new samples. Yeah. If the signal is repeating itself. So That's why we use the circular convolution, which is known as cyclic convolution, and the special case of periodic convolution. And this is actually, we use this convolution when there are two functions of which are periodic of the same period, yeah, which means it means they have to have the same number of samples. If it's periodic, it means the same number of samples keep on repeating, yeah. So this is what we are going to look at. This one, the representation is a bit different. Y of n is x of n, circular convolution. We use this n. This n means mod n, yeah. And so this is the mathematical formula for it. That is the summation of n varying from, k varying from 0 to n minus 1, yeah. X, because here we are not talking of infinity to infinity. We are talking about specific 0 to n minus 1. Because remember here, the two sequences are the same length, n, yeah. So x of k, h of n minus k mod n. And it's not h of n minus k mod n. Okay. It's not h of n minus k mod n. It is h of n minus k. Okay, I've drawn this, but normally it's supposed to be square brackets, but we have used the parentheses, yeah. So it's supposed to be n minus k mod n. Of course, you can see the difference. So the mod n is not of that function, it's of the variable, yeah. If you consider this to be the one which is varying, n minus k, yeah, of an independent variable. So because this is what is varying with this. So, well, there are two of them. So, but we are talking about y of n. So only k will be varying, yeah. So we have that. I hope we all understand modular arithmetic, yeah. Give you an example. If you are doing mode 4, it means you cannot have anything greater than 4. So whatever in modular arithmetic, whatever, if you have a number which is bigger than 4, you write that number as the remainder when you divide that number with 4. For example, suppose you have in mode 4 7. 7 in mode 4 is 3. It's just 7 divided by 4 goes to 1, remainder 3. Yeah. So 7 in mode 4 is 3. Yeah. 6 in mode 4 is 2. 5 in mode 4 is 1. 4 in mode 4 is 0. 1 in mode 4 is 1. 2 in mode 4 is 1. Is 2. 3 in mode 4 is 3. So mode 4 would only have 0, 1, 2, 3. It will not have 4. Because 4 is 0. 4 divided by 4 is 0. No, it's 1 remainder 0. So it's always with the remainders. So I'm sure you have done that somewhere along the way. Serafin, you have done that, haven't you?
Yes.
Yes, very good. Because this will keep on coming now in this circular convolution, but it also come next semester when you are doing um, error uh, detection and correction. We also use modulo arithmetic. Yeah. So now that you know that, let's now go to this example. But if you have a question, you can ask as we look at this example. So you are given these two sequences. Remember, these sequences have to be the same length. Yeah. So x of n is 2, 1, 2, 1, and h of n is 1, 2, 3, 4. So we are supposed to compute the circular convolution. Yeah. When we do the circular convolution, let's just work it out the way it is before we use, because we are going to use methods like the matrix method, and we see whether you get the same results. Yeah. So y of n is x of n mod h of n, which we have expanded to this, and what you are so y of n is y of 0, because this was have 4 samples. Yeah. You are doing mod n, so it will never have more than 4 samples. So it's y of 0, y of 1, y of 2, y of 3. So what is y of 0? Y of 0 means what? It means x, because this is 0, it just means x of k and h of minus k, but mod n. So this is x of 0. Remember, you are starting with k is equal to 0. This y of 0, this n, you are starting with k is equal to 0. Then this is 0, so we are talking about n minus k. So 0 minus k, we are doing it for 0. So it is 0 minus 0 mod 4. And what we are doing, actually, this is it should be 0 minus 0 mod 4. And there should be another bracket, because what we want is 0 minus 0 mod 4. Then you have the h. Yeah. So 0 minus 0 mod 4 means a 0. Yeah. So it means we are multiplying x of 0, which is the first sample here. This is x of 0. So we are going to multiply x of 0 and h of 0, because 0 in mod 4 is just 0. So an x and h of 0. X of 0 and h of 0. H of 0 is 1. So we are multiplying 2 and 1. X of 0 and h of 0. Because 0 minus 0 mod 4 is simply 0. Then the next one, we go to k is equal to 1. K is equal to 1, that is x of 1. H of n is still 0. This is minus 1 mod 4. Sorry about all this. This is supposed to be another bracket, because it is this minus 1 mod 4. Yeah? Minus 1 mod 4. So minus 1 mod 4 is what? Minus 1 mod 4 is, I think what we do is we look at the number that like for 7, we are looking at this smaller, so this should be minus, well, I know it is 3, but I'm going to wonder how I'm going to get it at 3. Yeah? For the negative numbers, we need to look at the number that is I'm trying to remember the modular of negative numbers. It should be the number that divides. We're looking at 4. How did we get this? Let's see. This eventually mode 4, the number we are looking at is 4, so it is 3. Well, it is 3. I'm trying to find out how to work it out. I'm trying to get the 3. That should be minus 1 plus 4. No, it can't be that easy. Yeah. Okay, let's continue. We know it is 3, so we are going to. I'm trying to remember the formula for calculating it. I know often it is 3, but I wanted to find out how do you actually work it out. So that is 3. So what you have is x of, this x of 1, which is 1, times h of 3, because this minus 1 mod 4 is 3. Yeah. Then that gives us 4. Then this other one is x of, so we are finished with this. This is x of 2, 0 minus 2. So minus 2, we know again, minus 2 should be plus 2. Yeah. So it will be h of 2, that will be times 3. Yeah. And the last one is minus 3. And we know minus 3 is 4. So that is not 4. It's mod 4. So minus 3 should be minus 3. It should be minus 3. This is h of, yeah, for the x we have no problem. Of course, the x we know this is 1. The last one for this is actually h of 1. Oh, yeah. Minus 3, minus 1 is 3, and minus 3 is 1. Yeah. That is minus 3 mod 4 is 1. So we are dealing with h of 1, which is actually this 2 here. So we multiply that, and when we add all that, it becomes 14. So the key is to understanding how to get the mode of each number, but the crucial one is learning how to get the mode of the negative numbers, because the positive numbers are straightforward. The negative numbers, I'm trying to see the general relationship. So that's the, yes. Somebody put up the hand.
Hello.
Yes.
I had a suggestion. You could use congruence.
Yeah.
So for example, 4 is congruent to 0 mod 4.
Yeah.
So you minus 1 on both sides, and you get 3 is congruent to negative 1 mod 4.
Okay. That will work for everything. That's the general. Okay. Thank you very much. Yeah. So that is that. So we do that for y of 1. It will be the same. You're just multiplying x of k. So for y of 1, you move again from k is equal to 0 to k is equal to 3. Yeah. Then again, you move, and of course, you use that value of n. So the value of n here is 1, so it will be 1 minus 0 is 1 minus 1, because n is 1, is 1 minus 2, 1 minus 3. k is going up to 3. Yeah. So once you do that, but all the time, remember, I think that's a mistake I made for all of them. It is all like this, yeah. Because if you did it the other way around, it will mean something completely different. Because h of, let's say, 0 is this one, and then if you do the mode of this, is just 1. So it will be completely different. So it is important that you understand this bracket so correct in your notes, so that it doesn't confuse you later. Yeah. That is for all of them. And of course, when it works out for all of them the same way, it's just repetitive. So that is how you do that's how you work out the circular convolution. Here we are working it out directly from the equation. You can do that also, by the way, also for the linear convolution. But what I was trying to emphasize is the difference between the circular convolution and the linear convolution. Because the circular convolution, you do mode n. Yeah. So I think there is no question there. But you can also use another method to do circular convolution, which we call the matrix method. And this matrix method is, you create this matrix, yeah, where you are simply sliding that, just this. Well, I don't know, I'm trying to put it in a general term, but this has used with this example. In this example, we have 2, 1, 2, 1, and h of n is 1, 2, 3, 4. So you create a matrix of one of these. I don't think it will make a difference. One of these x of n, an n by n matrix, and that matrix has got it starts with 2, 1, 2, 1, and then you start with 2, 1, 2, 1, 1. Yeah. What you are saying is, if you have, for example, you're having x of 0, x of 1, x of 2. Maybe I should not use x because I'm already using x here. Let's use m. You have m0, m1, m2, m3. The matrix you create, this is m0, m1, m2. There's a name this matrix is called, and this is m3. Then you have m1, m2, m3, m4. Somebody can remember what you call this matrix, because I think you also use it in media algebra somewhere. This is m1, m2. Oh, this is m1, m2. Sorry about that. It cannot be. You are starting with all this m0, m1, m2, m3. Then you start with m0, m1, m2, m3. So you multiply this matrix with this, and what you're going to get is actually the yn. So here we are. So this is 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1. And we multiply with this. So let's multiply out. So this is 2 plus, this is 2 plus, yeah, this is 2 plus 2 plus 6 plus 4. Yeah, that's 14. So again, this is 2 plus 2 plus 3 plus 8. And this is 2 plus 2 plus 6 plus 4. This is 2 plus 2 plus 3 plus 8. Ah, not 2, sorry. This is 1 plus 4 plus 3 plus 8. Yeah, 16. So you can see, using this method, we have managed to get the same answer. Yeah, so you can use the matrix method for circular convolution. I think nobody has a problem with multiplying matrices. Yeah, so long as I think the number of rows must be the same as the number of columns of what you're multiplying with. Yeah. Any questions so far? Looks like so far there's no question.
I have a question.
The convolution theorem is here. I saw you have already done this. I asked you this question and everybody was very okay with the convolution theorem. There it is. It's a very important theorem for us because I think we use it a lot.
Excuse me, sir.
Yeah.
Emmanuel
Yes.
has a question.
Yes.
Oh, I have a question.
Yes.
In the matrix the matrix method, I can see we've used the sequence of x of n
Yeah.
to do the 4 by 4 matrix.
Yeah.
Then we've used the sequence of h of n to do the column. Is there, are we supposed just to use the x of n for the 4 by 4 matrix and the other for the column?
Oh yes. If you generate what I thought you were going to ask whether we can use this one. I think it will give you the same answer. If we made a matrix of this, then we multiplied with this. It will give the same answer. Yeah, but once we use that matrix on one, normally we use it on the Hn or the H of n. I think okay, you have used it on the x of n. We use it on the H of n, and then we multiply, just multiply the other column. So long as, of course, it has to be the columns have to agree with the I mean the columns here must agree with the with this. The number of, okay, these are what? These are the columns, and these are the rows. Yeah.
Okay, thank you.
Yeah. But now that you say this, I was wondering what would happen. Suppose we did it the other way around. Suppose we did what? We did 1, 2, 3, 4. Then this 1, 2, 3, 4. 1, 2, 3, 4. With the convolution, is not supposed to change. Now let's see whether that will change. 1, 2, 1. Sorry, 2, 1, 2, 1. 2, 1, 2, 1. Well, it doesn't change because you are simply, it's just assembling in so this is 2 plus plus 8 plus 3. It's giving the same, it will give you the same thing. So it doesn't matter where you create your 4x4 matrix from either for next n or each of n. With the convolution, it doesn't change. Is that okay? All right. So the convolution theorem is very important to us because, as you can see, the convolution theorem is fairly convoluted. I mean, it's quite a lot of calculations. So what happens is even for the computer to do a convolution directly is actually very the complexity is quite high, especially because although we are showing sequences of 4 samples, in real systems, you don't work with the 4 samples. You work with long samples. Yeah, you work with very long samples, and if you have to do all this calculation with those samples, the mathematical complexity is quite high. There will be a lot of computations, and that will slow. That will result in computation time. What is the name for that one? The time that is taken within the processing device, yeah, to be very high. And we don't want that. We don't want, let's deal with propagation, delays. Let's not deal with computational delays. So that's why this becomes very important, because all you have to do is do the Fourier transform. And now, since we have new ways of doing Fourier transforms, yeah, the fast Fourier transforms. So you apply fast Fourier transforms and then do element-wise product, point-wise multiplication, yeah, which will be a much easier operation. Yeah. So we calculate the spectrum, we get the spectrum, the Fourier transforms, and then do point-wise multiplication. And of course, since what you really want is a convolution, eventually you have to do the inverse Fourier transform. Yeah. And why this is important is because once you do that, we can use even easy method of doing DFT. Even before we come to FFT, there are easy methods of calculating DFT by using what we call the endpoint DFT. Yeah, that's the next thing we are going to do. How to get the endpoint DFT, how to derive it and use it. And I think one of the most common endpoint DFT, I think, is the 4-point DFT. We are going to work it out. 4-point DFT. I think it is 1 1 1 1 1 1. I think this is my J minus 1 J, then this is minus 1 1 minus 1, and this is 1 J minus 1 J minus J. That's the smallest DFT, the 4-point DFT. What you are saying is you can use to get DFT of each sequence. You use this 4-point DFT. Yeah, you multiply that to give you the DFT of one sequence. Then get the DFT of the other sequence. Then multiply your DFTs. And then what you get, because you're doing element-wise multiplication, because you're familiar with element-wise multiplication, it means if you have x1, x2, x3, x4, and you have, let's say, h1, h2, h3. Of course, it will not be h, but I'm just thinking, for example, you know, whenever you see h, we always think about the impulse response. But just just take it just to be a h. So this will become x1 and 1. That's what you're talking about, element-wise product. x1 and 1, x2 and 2, x3 and 3, x4 and 4. I mean, x4 is h, not n. h4, yeah. So it becomes easy to do this, yeah. So you find the DFTs, and we are saying it's very easy to find the DFT because you can use the endpoint DFT. In this case, we'd use, in our case here, we'd use the 4-point DFT, yeah, to get, which is this, the 4-point DFT, to get the DFT of each of the sequences, and then we do point-wise multiplication or element-wise product, and then do the. So we are going to do this, and then do, of course, the inverse Fourier transform. Yeah. So you can also be able to get linear convolution from circular convolution. Yeah. In this case, you have got these two sequences. X of n is 1, 2, 3, 4, and h of n is 1, 2, 3. Because the sequences must be the same length if we are to use, you see, this is a circular convolution, which they don't have to be the same length. Sorry, this is a linear convolution. We want to do a linear convolution. They don't have to be the same length. But if we are going to use circular convolution to get linear convolution, then we need to make them the same length. That's what we are saying here. The sequences must be the same length for you to perform a circular convolution. So you have to pad them. And how do you pad them? Remember, when we do this, the length of the output sequence is L plus M plus minus 1 for the linear convolution. Is L plus M minus 1. So the length of the linear convolution of these two will be L 4 plus 3 minus 1. So that will be 6. So it means, and once you do circular convolution, the output will be the same length as the two sequences which are supposed to be of the same length. So you understand. So to do this circular convolution, you need to convert this, both of them, to L plus M minus 1. Because once you multiply them, they will give you the same length. Yeah. So you have to make them this length, because once you do circular convolution, there will be, the output will have the same length. So it means you have to make these sequences of the same length, and that length has to be the length of the output sequence of the linear convolution, which you know is supposed to be L plus M minus 1. So I hope everybody understands why we are doing this. So L plus n minus 1 is 6. So it means you have to pad these sequences with zeros so that they become of length L plus m minus 1. And then perform the circular convolution. So here they are. We have 1, 2, 3, 4. That becomes 1, 2, 3, 4, 0, 0. You just pad 2 zeros. This is 1, 2, 3, 4. Pad with 1, 2, 3. Pad with these zeros. So these are your two sequences. And as we said, you can make your L plus m minus 1 matrix from either of them. So in this case, I've just made from 1, 2, 3, 4, and then I multiply with this sequence. So this will give us 1. So if you multiply this, it's going to give us this. 1 times 0 times 0 times 0 times 0 times 0. So this is, so this becomes 1, that is 1, sorry, plus, not times, 0 plus 0 plus 0 plus 0 plus 0. This other one is 2 plus 2 plus 0 plus 0, everything else is 0. This is 3 plus 4 plus 3, everything is 0. This is 4 plus 6 plus 6, everything is 0. So that's how you do the math. Yeah. And what you are going to get is this one. Yeah. So that will be the length of your sequence. Yeah. That will be the length of your sequence. And it has got 6 samples. And we'll get the same if we did. Let's actually check whether we get the same. 1, 2, 3, 4, and 1, 2, 3. Okay. 1, 2, 3, 4, and 1, 2, 3. 1, 2, 3, 4, and 1, 2, 3. I'm using the tabular method. I could have put any of them in the place. So this becomes 1, 2, 3, 4. This becomes 2, 4, 6, 8. And this becomes 3, 6, 9, 12. So this becomes, that is 1, that is 4, that is 10, that is 4, 16, that is 17, that is 12. We still got the same thing. Yeah. So it means you can be able to find out the linear convolution through circular convolution. And to do circular convolution, it means you have to make your two sequences the same size and be the size of the output sequence if you are using linear convolution. Yeah. So does anybody have a question with this one? And of course, you can always do what you call, you can also do circular convolution from linear convolution. Yeah. Yeah. So I think here we are trying to work the other way. What we are saying, suppose you are, okay, this is not a very good example because we are trying to do the circular circular convolution from linear convolution. Of course, this is a good example because if you're doing circular convolution, you're going to have two sequences. But this is a procedure, but it does not work for this one. You need to get two sequences or the same length, you want to get circular convolution from linear convolution, work out the linear convolution, which means you're going to have 7 samples. If you have got 4, 4, it will be 4 plus 4 minus 1. You're going to get 7 samples. And that's what you are saying. You will get the trailing samples and add them to these samples. Like what you're doing yourself, 16, we're doing what? We are adding, what are we adding here? 1, 4, and we are getting these trailing samples, 17 and 12, and adding them to 1, 4. That's what we are getting here. We are getting the trailing samples and add them to 1, 4. But of course, that is if you have to convert circular convolution to linear convolution. But our sequences, of course, were wrong. So if I were to do that, I needed to have sequences of the same size, which of course is possible. It's just a matter of having these sequences. So if you have to do the circular convolution of these 2 sequences, you can get that from the linear convolution. You could have done the linear convolution, gotten this, and then get the circular convolution by wrapping around the trailing samples. I hope, because you see here, what we had was 3 samples, and when we did the linear convolution, the circular convolution, we got this. But we are saying you could have had these samples, where this sample is 0, and then we do linear convolution. But of course, and what I was saying is this answer will not be correct, because you are not going to get 6 samples. If you did this circular convolution, you'd get 7 samples, then do the wrap up. So although I did this example here, this is not it's not correct, because you do the circular convolution when you have the same length. So to do that, you have to do that to have this one with a 0, or this one with the. Actually, it will be the same thing. Come to think about it, it will be the same thing, only that the last sample will be 0. That's what I think. The last sample will be 0. Yeah. But you get, I think we are going to do examples of that in class. Yeah. But what I was trying to demonstrate here is the fact that you can do the wraparound. And we are going to see this wraparound just in a moment, especially when you're doing this, method of doing fast convolution. So fast convolution means doing FFT, yeah, and this is the whole idea is you have a very long sequence, you have a long block, you want to do convolution. A few things happen when you want to do a long convolution. It means, first of all, even you need to have that facility in your computing devices for storage, because it means you have to store the entire sequence, the long sequence, which you want to convolve with the impulse response. So what we do is we do block convolution. We call it block convolution, where we break that long sequence into manageable blocks. Then we take those blocks, we do convolution of each block. And the way you do that convolution of those blocks, and then of course add the outputs together. How you do the convolution of those blocks is where we use now the FFT to do the convolution of each of those blocks and then add them up. So you'll be performing FFT not on the long sequence, on the blocks which you have broken down, so that it is faster. Yeah. I think the best way to see it is using an example. And we are saying that how first of all use FFT. And remember, FFT is just a first method of the DFT. So we are here talking about DFT. And we are saying there are first methods of FFT. Yeah. So here we have x of n is 1, 2, 3, 4, and each of n is 1, 2, 3. And then we want to do y of n at convolution, which of course is x of, this just means x of k is x of n e to the, I think the general formula of course is, this is j 2 pi n 2 pi n k over n. Yeah. So it is, that's the general formula from 0 to n minus 1. That's the general formula for the DFT. We have to look at that next time. So it is for the, yeah, so it is this minus 2 pi nk over capital N. So for n is equal to 4, it is 2 pi nk over 4. Yeah. So for this case, we can work this out. Xk starting with x of 0, x of 1, x of 2, and just do the same way we were doing with the circular convolution. But you can also simply use this matrix. I think this is the matrix I was trying to write. Yeah, use this matrix. Yeah, this is a 4-point DFT matrix. We are going to show you how to derive it, and it works very well. So that is, use a 4-point DFT matrix. So x of k will be this. Okay. So we have found x of k for this. Then we do h of k. Now, to use this matrix, you need to add, we call it padding. You need to pad that sequence so that it has got 4 samples. And it's not a big deal, because that's what it means. When you say 1, 2, 3, it means the next sample is 0. That's why you are not including it. So you simply add that sample and multiply. So you're going to get this. And y of k, actually the way I've written is, yeah, y of k is simply multiplying this. I think I've written it the correct way. So, well, this is not correct, because this might mean like you are adding all this. Actually, it's supposed to be just multiplying direct. So you multiply this and this, it gives you the first one. You multiply this and this, it gives you the second one. Multiply this and this, because the way I've written it might mean that you're adding them. It might mean you are multiplying this and adding with this, which is not true. You're actually just multiplying the two. So the best way is just to put it in, put them in a column, as columns, okay? Because when you do this, it might mean multiply by this, add this, add this. Add this and then add this. which is not what we are doing. We are doing element-wise multiplication. So the best thing is, avoiding the confusion, is good to put this also in a column so to multiply directly. Yeah, and that would give us this. Yeah, yeah, because this is 10 times 6, 60. If you multiply this and this, it will end up giving us 8. It will give us 8. Yeah. Oh, this is minus 2j plus 2j times minus 2 minus 2j. So this is plus 4j minus 4j. I'll multiply these two with this. Then this is plus 4 minus times minus 1. So this is minus 4. And then multiply. So I'll just multiply this. Oh, only this is plus minus 2j plus 2j. Yeah, it's minus 2j plus 2j. Then multiply this. This is minus 4 plus 4. How do you get that? This is plus, isn't it? Or something wrong from here. This is minus, eh? So this minus, eh? That's why we went wrong. Let's see. Let's find out this. This is 1.
It's minus 2 minus 2j.
Oh, this is 2 minus 2j. Oh yeah, this is minus 2 minus 2j. And then this is minus 2 minus 2j. This is minus 2 plus 2j. No. Sorry. It was here, sorry. It is this one, and we are multiplying this one and this one. So the first one is minus 2j plus 2j. Okay? Where are we going? Minus 2j. The x. Yeah, x. Oh, minus 2 plus 2j. So this is minus 2 plus 2j. K is minus 2 minus 2j. Right, where are we? Minus 2 minus 2j. That is okay. So now let's work from there. So this is 4 plus, this is minus 4j. Then this times this is plus 4j. And then this is minus 4 times minus 1. J times 1, so it becomes 4, yeah. So you end up with 8. Yeah. So you can just do 0.8 multiplication, and somehow you end up getting rid of the j's, and that's what you get. And then of course do the IDFT of this one. IDFT is always a quarter, yeah, because of the 1 over n when you're doing the IDFT, yeah, a quarter, and then of course you're going to get is a quarter for this particular DFT matrix, because it's a 4-point DFT matrix. And then of course that matrix is almost the same. The only difference is the position of this minus j and plus j. Remember the other one, this was minus j, and this was plus j plus j. Now this becomes plus j minus j minus j. That's the only difference between the DFT and IDFT when you use the the endpoint matrix. So I think what we are trying to show here is that now when you do your block convolution, the various blocks you are going to use this method of using the DFT and then the IDFT. Using the DFT, do element-wise product, and then do the IDFT. So I think nobody has a problem with that. Don't worry about this one, because this one we actually going to derive it in class, and we will be using it. And we're even going to look at the 8-point DFT when you're doing the first Fourier transforms. So block convolution, of course, we are using block convolution. We are trying to reduce the length of the sequences, because whenever you do things like DFT, you don't want to do with very long sequences. Because remember, it means you have to first of all get the entire sequence. Just think about it. You have a sequence coming in, and you want to do a DFT operation in an actual system, yeah? It means you have to, if you have very many samples, you have to wait for all those samples to come in. And when you have all the samples, now you start. That itself is a delay. That's why you are trying to, first of all, break your sequence into small blocks. And we do that in all signal processing, whether it is error correction. You'll be getting your message when your analog message is converted to bits, to become a very long message. So we are always going to break it down to smaller manageable messages for signal processing. Where that signal processing could be anything. DFT could be error control, could be filtering. Of course, what you're talking about is filtering. When you talk about convolution, you're talking about filtering. Yeah. The HN is a filter. Yeah. So we are going to see how you do this. I hope you can be able to finish in the remaining time. You may not, but let's see how far you can go. At least you can do one of those methods. So we have got efficient algorithms for DFT, so we are going to use them. Multiplying the DFT, actually that's also very exciting, is multiplying the DFT actually corresponds to circular convolution or the corresponding sequence. So we must avoid time aliasing to recover linear convolution from the result of the IDFT. Yeah, we must avoid time aliasing. I think that's what we are going to see. We are going to see how we end up doing arithmetic to avoid that. So consider an input data xn of length L and a filter hn of length M. The linear convolution of the two sequences is supposed to give you that. So we are saying to avoid DFT, the length must be at least L plus M minus 1. Okay, we are saying what we are going to take. Yeah, the length which we are going to take and do the filtering, or do the, find out the DFT of, and then multiply with the DFT of HN must be of this length. And remember, when you talk of L plus M plus 1, we are not talking about the length of this long sequence, the long block which you are trying to find the convolution of. What we are trying to do, what? We are talking about the length of the smaller block which you have created. It must be L plus M minus 1. because computing the DFT of the entire, in this case, is impractical and will cause a long delay since you need samples to be input before filtering. Yeah, that's how filters work. You need all the samples you want to filter. You don't filter each bit that comes. You need to have the whole samples, yeah, and then do the filtering, yeah. So the first method is called overlap. There are two methods: overlap add and overlap save. And I think what we are going to do is we are going to first of all look at the overlap add method. It is the add. So in this case, the input signal is segmented in sections of length L. That's the L I was talking about, which is longer or equal to the length of the impulse response. So then each section is padded with m minus 1 zeros, where when we talk of m is the length of the impulse response. Yeah. So it's circularly convolved with the impulse response of length m padded with m minus 1 zeros. Sometimes when you read this, it may not make sense to you. But when you actually do work with sequences, then it becomes clear. Then the DFT of L plus M minus 1 can be used to compute the convolution. So you can use L plus M minus 1. So ordinarily, you can use an endpoint DFT of L plus 1. So N will be L plus M minus 1. So to use the endpoint DFT. The non-zeros point in the convolution will overlap by m minus 1 points, and these overlap points should be added together to construct the output. Let's go to the example. It is easy when you go to the example. So here we have x of n, which has got how many samples? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it 10? 4, 10. It's 10 samples. So, oh yeah, this is the length of sequence, which we call LS. Not confused with the L we are talking about. LS is equal to 10. Length of HN, that is the impulse response, which we are calling M, is 3. Now, remember when we do this, we are supposed to have, we end up getting LS plus M minus 1. Minus 1. That's what we should get. We should get 12 samples if we did the linear convolution. But remember, we are using this sequence of 10 samples as an example, but we are trying to break it into smaller ones. But ordinarily, it will not be a length of 10. It will be many thousands of samples, which you break down into shorter samples. But here we are using 10 as a as a long block, and we want to create shorter blocks, just for the purpose of demonstration of this overlap add. So let's consider 3 data points. We agreed that we want the number of data points you take to be at least equal to or longer than the impulse response. So you can use equal to or longer than impulse response. And of course, it makes sense because like now, you may want to use, depends on the DFT, endpoint DFT you want to use. If you wanted to use, for example, endpoint DFT, 8-point DFT, you would use this, you would use, the best way to use is what? You'd make, what would you make L actually? If you want this to end up with 8, then you use your L as 6. So what you have m minus 1 zeros to make 8, so that you use the 8-point DFT. Yeah, because you can use anything so long as it is above, is longer than the length of HM, is longer than m. So in this case, you have decided to use length is equal to m. Yeah, data points at a time, but then we are padding with m minus 1 zeros. So we're always going to pad with m minus 1 zeros. So the length you make here will depend on the end for the endpoint DFT you want to use. Yeah. And of course, endpoint DFT, although we work with 8 and 4, you can even have a 5-point DFT, 6-point DFT. Yeah. So there you are. You have x of 1. No, this is x. Oh, this is xi of n. This is a general one. Xi of n is just L data points, m minus 1 zeros. So x1 of n is 1 minus 1 0. So you are taking these 3 data points and padding with 0 0. Then you take these 3 data points, pad with the 0 0. Then take these 3 data points, pad with 0 0. And then take, of course, this is 1. So you have to first of all add 2 data points, then pad it. Because 1 will be the same as, it means the next one is 0. So just add 0 0, then pad it. Yeah. And then we do what? We do the circular convolution. This one here. So we are showing that you do circular convolution. Of course, you can get that through circular convolution, or you could simply get this through using the DFT. Use DFT and then use IFT to make it faster. You see, you're only using DFT to make it faster, but here I'm just simply using circular convolution method. Yeah, the method you use because the samples are not so many. But you'd get the same answer if you found y1 of k and h of k. So you get your y1 is the output. It should have been x1 of k and h of k. Then find element-wise product. Then do the inverse for the transform. But we are using we have decided here for this, demonstrating this. We just use the circular convolution. It will give you the same answer. So let's use the circular convolution. We know our HN is just 111. So that's what we are doing. We use HN. So 111, 111, 111, 111. Yeah. Remember this, we have used H1, we have used H, the lengthened H, which has got 2 m minus 1 zeros. Yeah, that's what we have done. So that gives us that. When you multiply that, y2, the second part of the sequence, this one gives us that. Then there is part of the sequence. Where are they here? 0, 1, 2. 0, 1, 2 is this one, gives us that. And the last one is this one. 1, the 2 part is 0, and then plus 1 0. So we have that. Then what we do is we add them. So y of n will be y of 1n. Then we have this last m minus 1 samples are added to the first m minus 1 samples. Yeah. Like that, like that. So if we add this, what you are going to end up with is that. If you add this, so this is 1, 0, 0. This is 0 because this is minus 1 plus 1 is 0. This is 2. Then this is 4. Then we add the last m minus 1 samples with the first m minus 1 samples. We get 3, 3. Yeah. We get 3. We get 4. 3 plus 1. This is the first. You're adding the last m minus 1 samples of y to n. Yeah. So, and the first m minus 1 samples of y3n. So 4, 3, 1, and of course 0, 0. These 0, 0 are coming because of those 0, 0s we added to 1. Then we expect it to be 12 samples. So you discard the last 2 samples. So this will be 12 samples. These are 14 now. So you discard the last 2 samples. And of course, this one, as I said, is coming in because of these 2 samples we added here. Yeah. So we are discarding the last 2 samples, and we are going to get the 12 samples. It will be this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It will be LS plus M minus 1. And that is the method we call overlap add method. Yeah. Are there any questions? Because we won't look at overlap save. It's almost similar, but we can look at it in the class, in the next class.
Yes, I have a question.
Yes.
When you are looking at we were dealing with the FFT,
Yeah.
and we used the 4-point DFT.
Yeah.
I was a bit concerned. Will the FFT yield a similar solution to if we use, let's say, the DFT?
Like if you use DFT.
Yeah, if you do DFT and FFT, are the results the same?
Yeah, if you use FFT, you see, FFT is just a, what do you call it? Just a first method, which you go and look see how it works. FFT just does DFT, but there's a first method of doing FFT. Yeah, but I was thinking your question will be, will you get the same answer like what we have done with what you have done? Because what you have done, we have not used FFT. What you have done, we have just used the method for circular convolution, but it will give us the same answer. But you see, for this short one, it's a lot of work to do the DFT. But for a long sequence, of course, it will be much easier to do the DFT and then do the IDFT, sorry. Yeah. But for this one, we just use the circular convolution. Is that okay? Or have I left you more confused?
Could you kindly scroll to the example where you first introduced the 4-point DFT, the matrix with the 1s and the J's?
Yes. Where was that matrix? Where did we talk? Here.
Yeah.
So
if this example we did with the circular, for example, would it still yield 18, 16, 10, and 16?
Exactly. If we do that, what we will do is those 2 things we are multiplying, instead of doing a circular convolution, we would have done, first of all, the x1. You see, in that case, we are talking about x1n, x2n, x0n. I mean, we are starting, okay, no, for that we can call them x1, x1n, x2n, x3n, x4n. Okay. So because we have got 4, we have divided the entire length into 4 blocks. Yeah, each of 3 samples. So what we should have done after making it that length, of course, we can't use 4-point DFT in this case because we can't use 4-point DFT. In fact, the way it is now here, if you want to use the 4-point, we would use 5-point DFT. Yeah, you get it? We'd use a 5-point DFT. Although we use the 8-point DFT and 4-point DFT because it is easy to explain an even number of DFT, but you can still have even a 4-point DFT, 5-point DFT. So if you use a 5-point DFT, we would get the same thing, but we don't have even the 5-point DFT. The one we have is 4-point DFT. When can you use a 4-point DFT? Is, for example, if you have 2 samples, I think you can use 4-point DFT because you can use 2 samples and then we add m-1 samples. You can, in fact, you can use how many samples? Can we? I think we can. Suppose this was just 2 samples. So you can take 3 samples and then add m-1 samples, which is 1 sample, and then use DFT. Are you seeing what I'm saying? If you want to use 4-point DFT, you can't do it with these 3 samples because you can't take less samples than m. So you have to take m samples. So when you add, L has to be equal to m, worst case scenario, the 3 samples. Then you add your m plus 1 samples, so you get 5. So, but for example, M5, 5-point DFT will be a very complicated one. It's normally used to better to use the 4. I think why you use 4 and 8 is because they are very simple. They just either have a -1 and -j, very uncomplicated. And 8 also the same way. If you use the 5-point DFT, which you could use, but even its calculation is more complex for us. But you are saying if a computer is doing this and dealing with a longer sequence, it is still better to use the FFT, or rather the fast method of doing DFT. Yeah, but this one you can't do because you can't use for DFT. Unfortunately, you have seen, we can't use because this is 5. So you can't use for DFT with this method. I mean, with this particular problem. If you are to use DFT and we want to use, then you can use 8-point DFT. That's what I'm saying. 8-point DFT, you will get the same answer whether you do the circular convolution method or you use the 8-point DFT and then use the 8-point IDFT. But then that would have to be a bit different. It will mean you have to take 6 samples at a time. So you take these 6 samples and then take these 4 and pad with 2 samples. Then add m-1 samples to make it 8. So at each block has 8. So x1 8, x1n has 8, and of course now it will just be x1n and x2n has 8. Then you use the 8-point DFT and then do the IDFT. You'll get the same answer. Yeah, we have 2 minutes. I think we can look at it more in the next class. In fact, you can try to work this with 8-point DFT and see what you would get. Yeah. Whether we would get the same answer. Actually, if you get the same thing as you get with that, with a 6 point, with a 5 point circular convolution. Yeah. Yeah. Is that okay?
Yes, it is. Thank you.
Okay, so we will stop there. Let's meet next Wednesday. Our Good Friday and weekend. And the earlier part of the week, then we meet on Wednesday. And by the way, let's just post our registration on the chat. That will be our roll call. So once you post that, you can leave at your own